Okay, we are just discussing about optical activity of some selected organic compounds. आपण यामध्ये काही ऑर्गॅनिक कंपाऊंड्सचं डिटेल ऑप्टिकल ऍक्टिव्हिटी स्टडी करतोय. We have already studied first compound lactic acid as well as tartaric acid. Now let us see one more 2,3-dihydroxybutanoic acid. We are going to discuss optical activity of this one more compound 2,3-dihydroxybutanoic acid. Okay, this is the structure of 2,3-dihydroxybutanoic acid CH3, CHOH, CHOH and COOH. Our first question is it having any chiral carbon? Now what's about the methyl carbon? Yes, it is not chiral in nature. But what about the next one? Now this carbon, I will mark star. This carbon is attached to the OH, then methyl group, third one is the hydrogen, and fourth that whole group. Means it is attached to the four different atoms or group. Hence that carbon is a chiral in nature. It is called chiral center, or it is also called as the asymmetric carbon atom. Now what's about the next one? This next carbon is also attached to the four different atoms or group. One is the OH, second is the hydrogen, third is the COOH, and fourth that whole group. Means that carbon is also chiral in nature, but the carbon of COOH, this is not asymmetric. This is not chiral center because it is not attached to the four different atoms or group, and thus 2,3-dihydroxybutanoic acid having two chiral center, and therefore according to the formula 2 raised to n we can calculate number of possible stereoisomer. Here n is number of chiral center. Now let us put the value 2 raised to n is equal to 2 raised to 2, means there should be 4. 2 raised to 2 means 4, and thus that molecule having four possible stereoisomers. Now let us see what are that four possible stereoisomer for the same compound. Okay, this is the first possible stereoisomer. First one, that two OH groups are shown at the same side. They are shown at the right hand side, same side. While suppose this is the second isomer, second stereoisomer, here that two OH groups are shown at the left hand side, while in the first case they are shown on the right hand side. Okay, this is the second possible stereoisomer. Now let us see one more. Here first OH is shown at the right hand side and second OH is shown at the left hand side. This is the third possible stereoisomer, while fourth one here exactly vice versa. First OH at the left hand side and second OH at the right hand side. Okay, these are the four possible stereoisomer. Actually that stereoisomer having different arrangement of atoms or group around the chiral center, and these are the four possible stereoisomer for 2,3-dihydroxybutanoic acid. Now let us see just a relation between that different isomer. यामधलं relation आपण बघूया. What's about the first and second? Actually first and second both having chiral center. They having chiral carbon. There are two chiral carbons. Now there is no any element of symmetry. They do not having plane of symmetry. There is no center of symmetry. There is no alternating axis of symmetry, and thus that first and second contain a chiral carbon and there is no any element of symmetry. Therefore they show optical activity. They are optically active, and that these are the optical isomers. They are called optical isomers. Okay, now what is the relation between first and second? Okay, here suppose this is the mirror. Suppose this is the mirror in between that two. Then one isomer looks the mirror image of another. यामध्ये एक इमेज किंवा एक आइसोमर हा दुसऱ्याची मिरर इमेज आपल्याला वाटतोय. One isomer looks mirror image of another, and also suppose एकाला आपण उचललं आणि दुसऱ्यावरती मॅच करायचा प्रयत्न केला. म्हणजे इथं OH आहे, याच्यावरती हायड्रोजन, म्हणजे दे डू नॉट मॅच विथ इच अदर. That means first and second, they are non-superimposable mirror images of each other. First and second, they are non-superimposable mirror images of each other. Hence, they are called enantiomers. They are optical isomers and they are non-superimposable mirror images. Hence, they are called enantiomers. Now, out of which one is a dextro. One is a dextro. It can rotate the plane of PPL in clockwise direction, while another is the new isomer. It can rotate the plane of PPL in anti-clockwise direction. Okay, and this is just about the first and second. Now what's about the third and fourth? Suppose this is again actually third and fourth. Again they having chiral carbon. Also there is no any element of symmetry. Third and fourth also having chiral carbon, and there is no any element of symmetry. Therefore they are also optically active. They are also optical isomers. Now what is the relation between them? Here that two are third and fourth, that two are mirror images of each other. म्हणजे सपोज OH समोर आहे, आरशामध्ये आपल्याला समोर दिसतोय, त्यानंतर इथला OH बॅक साइडला आहे, इथे मिरर मध्ये आपल्याला बॅक साइडला दिसेल. मीन्स दॅट टू आर मिरर इमेजेस. आणि यामध्ये एक इमेज आपण उचललं आणि दुसऱ्यावरती मॅच करायचा प्रयत्न केला, दे डू नॉट मॅच विथ इच अदर. मीन्स थर्ड अँड फोर्थ आर ऑल्सो नॉन सुपरइम्पोजेबल मिरर इमेजेस ऑफ इच अदर, and therefore they are also enantiomers. They are also enantiomers. One is a dextroisomer, means which can rotate the plane of PPL in clockwise direction, while another is a leoisomer, which can rotate the plane of PPL in anti-clockwise direction. Okay, this is just about the relation between first and second and third and fourth, and these are the pairs of enantiomers. These are the pairs of here first and second and third and fourth. These are the pairs of enantiomers. Okay, now this is just a relation between first and second. Suppose there is an equimolar mixture of first and second, means that mixture is called racemic mixture. It is racemic modification, and therefore it is optically inactive. It is optically inactive. Similarly, equimolar mixture of third and fourth, it is also optically inactive because it is also equimolar mixture. Okay, now let us see relation between first and third. यामध्ये फर्स्ट आणि थर्ड या दोन्ही मध्ये काय रिलेशन आहे? व्हॉट्स अबाउट द रिलेशन बिटवीन फर्स्ट अँड थर्ड? आर दे मिरर इमेजेस ऑफ इच अदर? फर्स्ट अँड थर्ड, दे आर नॉट मिरर इमेजेस ऑफ इच अदर. फर्स्ट अँड थर्ड, they are not mirror images of each other, and such stereoisomers which are not mirror images of each other are called distereomers, and thus first and third are called distereomers. Similarly, first and fourth, पहिला आणि चौथा, first and fourth, they are also not mirror images of each other, hence this is also called pair of distereomer. Similarly, second and third, they are also not mirror images of each other. Similarly, second and fourth, they are also not mirror images of each other, and hence these are the pairs of distereomers. Now there are four pairs of distereomer. First one is the first and third, then first and fourth, second and third, and second and fourth. These are the pairs of distereomers. Okay, this is just about the optical isomerism in the 2,3-dihydroxybutanoic acid. Okay, in first step we have studied, is it having chiral carbon? Yes, that molecule having two chiral carbon. Therefore, according to formula 2⁻n, it has the four possible stereoisomers. These are the four possible stereoisomers for 2,3-dihydroxybutanoic acid. Okay, we have studied relation between that stereoisomers. First and second, they are non-superimposable mirror images, hence they are enantiomers. Then third and fourth, they are also non-superimposable mirror images, hence they are also called enantiomers. One is dextro, second is the leo. Similarly here also, one is dextro, second is the leo. Okay, and these are the pairs of enantiomer, while equimolar mixture of that dextro and leo isomer is a racemic mixture. While we also studied relation between first and third, first and fourth, second and third, and second and fourth, and these are the pairs of distereomers. Okay, this is just about the optical isomerism in some selected organic compound, geometrical isomerism. Now let us say example of same compound I have taken in the introduction, CS3, then there is CH, double bond CH, CS3. That compound is a 2-butene. Now that compound having two possible stereoisomers. Suppose this is the first one and this is the second one. Now what is the difference between that two? In first case, that two methyl groups are present. Here that two methyl groups are present at the same side of double bond. While in the second stereoisomer, that two methyl groups are present at the opposite side of double bond. Means here arrangement of atoms or group around the double bond is different. Both are the 2-butene. Both the isomers having same molecular and structural formula. But arrangement of atoms or group around the double bond is different, and that isomers are called geometrical isomers, and that concept, that phenomena is called geometrical isomerism. Best example is the 2-butene. It having two isomers. One is called cis and second is the trans actually. Okay, now let us see one more example. I will take example of cyclic compound. This is 1,3-dimethyl cyclobutane. This is 1,3-dimethyl cyclobutane. Now here, what is the difference between that two? Both are the structures of 1,3-dimethyl cyclobutane. There are 4 carbon atoms, 1, 2, 3 and 4 carbon atom. Here also 4 carbon atom, but 2 carbons having again methyl group. Therefore it is dimethyl cyclobutane. Okay, now what is the difference between that two? In the first case, that methyl groups are present at the same side of ring. 2 methyl groups are present at the same side of cycle. While in the second case, that 2 methyl groups are present at the opposite side of the cycle. And such isomers are called as the geometrical isomers. Geometrical isomerism is also observed in compounds which containing cycle. ज्यामध्ये रिंग आहे, not only double bond. फक्त डबल बॉन्ड असणारेच कंपाऊंड geometrical isomerism दाखवतात असं नाहीये. The compounds which having cycle, they also show the geometrical isomerism. मग मगाशीचं जे डेफिनेशन होतं ते थोडंसं मी एक्सटेंड करतो. The stereoisomers which having same molecular and structural formula. The stereoisomers which having same molecular and structural formula, but different arrangement of atoms or groups around, double bond or ring are called geometrical isomers, and phenomena is called geometrical isomerism. Now in this 2-butene, that 2 methyl groups are present at the same side of double bond. That 2 identical groups are present at the same side of double bond. Then that isomer is called cis isomer. Means if that geometrical isomer having identical groups on the same side of double bond or cycle, then it is called cis isomer. While if identical groups are present at the opposite side of double bond or cycle, then it is called trans isomer. This is the trans 2-butene, while this one is the cis 2-butene. Okay, and therefore that isomerism, geometrical isomerism, is also known as cis trans isomerism. It is also known as cis trans isomerism because one isomer is a cis and second is the trans. Therefore, it is also called as the cis trans isomerism. And generally, that type of isomerism is observed in compounds which having C double bond C, C double bond N, and compounds which having ring, that is cycle. That compound can be show the geometrical isomerism. Now let us see, this is just introduction. What is meant by geometrical isomerism, what is cis isomer, what is trans isomer, etc. Now let us see cause of geometrical isomerism. Cause म्हणजे आपण काय स्टडी करणार आहोत. What is the reason of geometrical isomerism? Why the compounds which having double bond? Shows the geometrical isomerism. Now let us see simple general example. Suppose this is the general organic compound and there is a C double bond C. यामध्ये carbon double bond carbon आहे. First carbon having 2 single bonds, 1 double bond, and here also double bond C, again 2 single bonds. What's about the nature of this bond between 2 carbon? 2 कार्बनच्या मध्ये जो बॉन्ड आहे त्याचं नेचर तुम्हा सर्वांना माहिती आहे का? Now what is the hybridization of that carbon? Hybridization of this carbon is sp2, right? 1 s orbital and a 2p orbital undergo mixing and recasting. Generally, example of that double bond containing compound is ethene, cs2 double bond cs2. In ethene, the hybridization of both the carbon is sp2. Suppose that first carbon having sp2 hybridization means there are 3 hybrid orbital. Now that hybrid orbital of carbon overlaps with the hybrid orbital of another carbon to form carbon-carbon sigma bond. Suppose this is the carbon-carbon sigma bond, Similarly, that hybrid orbital of carbon overlaps axially with another atom to form second covalent bond. Then it again forms third bond. Similarly, this carbon also forms two more covalent bond, and thus there is a formation of sigma bond. Okay, now we will concentrate the bond between the two carbon atom. Between the two carbon atom, there is a double bond. And how the first bond is formed? It is formed by the axial overlapping of hybrid orbital. Okay, now in the case of sp2 hybridization, we know that both the carbons also having unhybridized orbital, and this is the unhybridized 2pz orbital which lies perpendicular to the main plane. First carbon, this is the 2pz orbital of second carbon. Now these 2pz orbitals of first and second carbon, they overlap sidewise with each other. This is the sidewise overlapping to form pi bond, and there is the formation of pi bond. Thus in between the two carbon atom, there is a double bond, while one is a sigma and second is the pi bond. In between the two carbon atom, there is a double bond. One is a sigma bond which is formed by axial overlapping, while second is the pi bond which is formed by sidewise overlapping of unhybridized 2pz orbital. Now due to this situation, rotation about carbon double bond carbon is not possible. Suppose there is a carbon single bond carbon, रोटेशन इज पॉसिबल, तिथं रोटेशन होऊ शकतं, पण इथं मात्र कार्बन डबल बॉन्ड कार्बन भोवती रोटेशन जे आहे इट इज नॉट पॉसिबल. अँड ड्यू टू दिस the positions of, due to this restricted rotation, this is called rotation is not possible, means there is a restricted rotation, and due to restricted rotation the positions of atoms or group around the carbon are fixed. म्हणजे सपोज या ठिकाणी ज्या पोझिशन्स आहेत, इथं सपोज या ठिकाणी CS3 ग्रुप असेल, दिस इज द पोझिशन ऑफ हियर इफ देयर इज हायड्रोजन ॲटम, सपोज देयर इज अ CS3 ग्रुप, इथं CS3 ग्रुप आहे आणि खालच्या बाजूला हायड्रोजन आहे, मीन्स दिस इज द सिस आयसोमर, राईट. दॅट पोझिशन्स ऑफ ॲटम्स ऑर ग्रुप रिमेन्स फिक्स्ड, त्या बदलत नाहीये. And therefore geometrical isomerism is observed. म्हणून geometrical isomerism आपल्याला आढळून येतो. Okay, in alkene, in double bond containing compound, there is one sigma and one pi bond, and due to this situation, rotation about carbon double bond carbon is not possible, and due to restricted rotation, the positions of atoms or group around the double bond remains fixed. म्हणजे सिस असेल तर सिस राहते, ट्रान्स असेल तर ट्रान्स राहते, आणि म्हणून आपल्याला geometrical isomerism आढळून येतो. And thus there is a geometrical isomerism in that compound. This is the cause of geometrical isomerism. ठीक आहे. आता यामध्ये आपल्याला फक्त एक कंपाऊंडचं geometrical isomerism स्टडी करायचं आहे इन डिटेल. geometrical isomerism with respect to C double bond C असं हेडिंग आहे. कार्बन डबल बॉन्ड कार्बन मध्ये that compound having double bond, how many carbons are there? 1, 2, 3 and 4, means parent alkane is a butane. Parent alkane is a butane. Okay, now there is one double bond, therefore I have written butene. But at the end there is two COOH group, therefore it is called butene dioic acid. Name of the compound is a butene dioic acid. Okay, this is the butene dioic acid. Now let us see geometrical isomerism in that compound. This is the first geometrical isomer. Now let us see second isomer. This is the second isomer. Actually both are butene dioic acid, both having same molecular and structural formula, but we have shown the different arrangement of COOH group around the double bond. In one case two COOH groups are present at the same side, while in the second case that two COOH groups are present at the opposite side. Suppose they are present at the same side, then it is called cis isomer. Okay, and this cis isomer is also called as the malic acid. It is malic acid. Okay, then if two COOH groups are present at the opposite side of double bond, then it is called trans isomer, and it is called fumaric acid. It is trans butene dioic acid is called fumaric acid, and cis isomer is called malic acid. That two geometrical isomers having different physical and chemical properties. They may be shows different chemical and physical property. Let us see some examples of physical property. काही examples आपण बघूया physical properties example. Suppose trans isomer having high melting point than cis isomer. Melting point of cis isomer is 300 degree Celsius एवढा आहे. तर melting point of trans isomer is 130 degree Celsius. Means there is a difference in their melting point. There is a large difference between melting point, and thus the physical properties of geometrical isomers may be different. Now let us say about the solubility. आपण दुसरा क्रायटेरिया बघूया, solubility. ट्रान्स आयसोमरचं एक्झाम्पल घेऊया, फ्युमॅरिक ऍसिड. त्याची सोल्युबिलिटी आहे 0.7. इज सोल्युबिलिटी 0.7 पर 100 ml. म्हणजे 100 ml जर वॉटर असेल तर त्यामध्ये फक्त 0.7 ग्रॅम एवढा फ्युमॅरिक ऍसिड किंवा ट्रान्स आयसोमर सोल्युबल होतो. वाईल इन केस ऑफ द सिस आयसोमर सोल्युबिलिटी इज व्हेरी हाय. खूप जास्त प्रमाणात तो त्यामध्ये सोल्युबल होतो. या ठिकाणी सोल्युबिलिटी बघा जवळपास 78 ग्रॅम. दॅट सिस अँड ट्रान्स आयसोमर, दॅट जॉमेट्रिकल आयसोमर हॅव्हिंग डिफरंट फिजिकल प्रॉपर्टीज. त्यांच्या फिजिकल प्रॉपर्टी या वेगवेगळ्या असू शकतात. आताच तुमच्या समोर 2 एक्झाम्पल्स ठेवला, आणखीन एकदा दाखवतो. सपोज दिस इज द मॅलिक ऍसिड, त्याचा आहे 130 डिग्री एवढा. फ्युमॅरिक ऍसिड त्याचा आहे 300 डिग्री एवढा. त्यानंतर मॅलिक ऍसिडची सोल्युबिलिटी आहे 78.8 ग्रॅम एवढी 100 ml पाण्यामध्ये, आणि याची आहे फक्त 0.7 ग्रॅम एवढी फ्युमॅरिक ऍसिडची ट्रान्सची. तर दॅट दे आर हॅव्हिंग डिफरंट फिजिकल अँड केमिकल प्रॉपर्टीज. ओके, नाउ लेट अस से अबाउट द केमिकल प्रॉपर्टी. मी केमिकल प्रॉपर्टीचा एक एक्झाम्पल घेतो. सपोज दिस इज अवर सिस आयसोमर, दिस इज द मॅलिक ऍसिड. ओके, सपोज इट इज हीटेड ॲट टेम्परेचर 140 डिग्री सेल्सिअस. त्याला आपण हीट केलेलं आहे 140 डिग्री एवढ्या टेम्परेचरला. मग या ठिकाणी काय होतं हिटिंग केल्यानंतर? इट अंडरगो डिहायड्रेशन. When a malic acid is heated at 140 degree Celsius temperature, it undergo dehydration. OH from one COOH and hydrogen from another COOH form H2O. त्यापासून वॉटर मॉलिक्यूल तयार होतो. While this molecule undergo cyclization and we get the cyclic compound. म्हणजे वरचा CO मी इथं दाखवलेला आहे, वरचा CO. त्यानंतर खालचा हा CO इथं दाखवतो मी, CO खालच्या बाजूचा. त्यानंतर याच्यावरती आणखी एक ऑक्सिजन आहे, तो ऑक्सिजन आपण इथं सेंटरला दाखवूया. अँड दिस ऑक्सिजन नाउ फॉर्म बॉन्ड विथ धिस वन, अँड दिस इज कॉल्ड malic anhydride. This is called malic anhydride, and thus malic acid, that is cis isomer, on heating undergo dehydration. This is called dehydration because there is a loss of water. It undergo dehydration and cyclization, and we get the malic anhydride. But what's about the trans isomer? In trans isomer, the 2 COOH groups are away from each other, but in cis isomer they are close, and therefore it undergoes cyclization. But in the trans isomer, the 2 COOH groups are away from each other. Therefore, when it is heated at 140 degree Celsius temperature, it do not undergo cyclization. There is no anhydride formation. यामध्ये मात्र anhydride formation होत नाही. There is no anhydride formation. Okay, this is just about the how the geometrical isomers having different physical and chemical properties. Okay, we are just discussing about a very important topic from the organic chemistry, stereochemistry of organic compound.